Today we will talk about the fourth type of nuclear reaction, which is the radioactivity, which is known in other words as radioactive decay. The other three types are the transmutation, nuclear fission, and nuclear fusion. We discussed those in the previous video, so if you have any question, please refer to the information that is on that video. It is known that there are 4 radioactive decays. First one is alpha decay. Next one is beta positive, which is in two forms: beta particle, which can be beta positive or beta negative, and next one is gamma. If the first two are particles, so alpha decay is just the helium particles. Next one is a photon because it's a gamma. Now alpha, it's positively charged. Alpha decay is positively charged. We know it's the helium, nucleus of helium. They are ejected at high speed. At high speed, and the penetration is not that at a high range. It's about a few centimeters in air, and it can even be stopped by a sheet of aluminum foil, so low penetration. Beta particles, either positive or negative, those are high energy electrons or positrons, so they have high energy. Electrons or positrons that are ejected from nucleus. They have different speeds, and sometimes it's even at the speed of light, so the speed in which they are moving is different. And then they have few centimeters in an aluminum foil, so I have a higher penetration than alpha particle, but not that extremely high. So higher penetration than alpha particle. But the gamma rays, on the other hand, are photons. Okay, so they have a very short wavelength. Okay, very short wavelength, and they have no charges. So gamma has 0 charge and 0 mass. Their energy is different because depend on the wavelength that they have. Energy varies depending on the wavelength, and they can penetrate few centimeters, 30 centimeters, up to 2 kilometers, especially in air. Okay, so when we talk about the charges for beta particle, as I said, there are 2 types that we will see. It can be positive or negative. So if alpha particle is the same as saying helium-24, for beta negative, we will have the electron, which is with charge -1 and 0, And for beta positive, which is positron, will be with charge +1 and a 0. A very simple method to identify and classify those is through a magnetic, when we put them through a magnetic field. So if those charges are coming into a magnetic field, let's suppose that they are coming into a magnetic field that is into the page, then gamma ray being no charge will go straight. So gamma ray. Alpha particle will go up. Beta negative will go down. And beta positive will go up with the same radius as beta positive. Even though that here doesn't look like it is the same, but it's the same radius because we will see they are antimatter of each other. Okay. So when the radioactive decay isotopes undergo the decay, the radioactive decay, then very often a new isotope form is created, which is in most cases is non-radioactive and it's very stable. Let's see a picture of in which we are looking at what is happening. So as you see here, we start with uranium-238, and then an alpha decay is released, and then a beta negative, and then alpha, until we come to those elements, and they are, as soon as they are releasing an alpha, they still are not quite stable, so they release more and are release until they come to PB 206. So all of those transformations, though are made based on the, or keeping in mind the conservation law of charges, which we talk about it in the previous lessons, and the other one is conservation law of masses. And those two law are saying that the charges are not created, not destroyed, which is translated into nuclear reactions as the sum of the charges in the parent side is equal to the sum of the sizes on the daughter side, or sometimes we call parent as the reactant and product, just to be confirmed with what we have used in chemistry. So this is we start with uranium and then we end with Pb, which being a stable form of isotope. Let's see now if we can write a complete nuclear reaction equation for the following beta decay of thorium 234. So it's releasing a beta negative. And then what is happening? What is the element that is formed? So when we have thorium 234, thorium is 234, yeah, is on the 90th place on the periodic table. So the way that we write in a proper notation will be like this. And then what it is happening, it is releasing beta negative. So beta negative, you can say beta negative, or you can say an electron. So the new element that is formed is element X with a charge of Z and atomic mass of A. Very often you will see the same reaction written into the form thorium 234 is releasing a beta negative, and an element X with Z number of charges or number of protons and A number of nucleons. It is the same thing. So when we are applying the conservation law of charges, then what we will do, charges on the parent side, which in parent side is only this one here, so 90 is equal to negative 1 plus Z. So adding 1 in both sides, then Z will be equals to 91. And when we take a look at the periodic table, on the 91 place is protractium, so PA. Okay, so now let's apply the conservation law of masses. So atomic mass on the parent side is equal to atomic mass on the daughter side, which daughter side is this one here. So will be 234 is equal to 0, but is the charge or the atomic mass of the electron, and A. So from here we can find that A is 234. So now the new element that is formed after beta negative is decayed is protractium 234. The complete reaction will be written on this form. Thorium 234 is releasing, you can say, a beta negative, or you can say an electron -10. Both of them are correct. And then is protractium 91 234, which is still an excited nucleus, and this star here identify that excitement. However, beta negative decay has one let's say case in which the conservation law of charges and the conservation law of masses is not quite true the way that we see it here. So it was noticed that for helium or alpha particle, the conservation law of charges and the conservation law of masses was very well applied, but when it comes to the beta negative or beta positive, there was something that another particle that was identified, and this is a second generation of particles that is identified, and this mysterious particle is known as the neutrino. So to begin with, it was understood that beta particle was produced when a neutron and in the nucleus is converted into proton. So what do we have is a neutron is converted into a proton, 1 and an electron, -1 0. If we see the conservation law of charges or the conservation law of masses, then it looks like it is applied. However, Paul is in order to satisfy, Paul is a scientist that we're dealing with the subparticles, and then he detected that there is a new particle that was released as well. It was very difficult to detect initially, and it was a neutral particle, but still it is a particle that is detected, and that particle is known as a neutrino. So the way that is written is like this. So the neutrino particle is a massless particle, okay, no mass. It looks like photon and it is neutral, so no mass and no charge. Fermi called this particle neutrino, which means like a neutral one. But it is the symbol for it is this Greek letter mu, and the proper equation of a neutron that is it is creating a proton and an electron is this one here. Now, neutrino, proposed by Pauli and supported by the work of Fermi, received a many mixed reception in the world of physics. It seems like a mystical particle, and it was weird to accept it. According to the conservation of momentum, the electron should shoot off in one direction and proton in the other opposite direction if there is no other. So we start with a neutron here and 0 1, and then if there is no other particle like neutrino that was produced, let's say, then if the electron is going on this direction, in the same direction with the opposite, in the opposite direction and the same magnitude, proton should be released. But this was not actually not the case. So what actually happened when we had the neutrino here, the electron was going in one direction and proton was going on the other direction. And to compensate for this, in order to satisfy the conservation law of charges, then we have to have the momentum of neutrino here. Okay. It's just a neutrino. It's like this. Okay, neutrino. So this made them. There is more into it as the angular conservation of angular momentum, which particles have, and they have something that is known as spin. So that is measurement into quantum scale of measurement. And the proton and electron both have a spin of 1/2, so that the angular momentum, however, exists in two variation, clockwise, which is positive 1/2, and counterclockwise, that is negative 1/2. The conservation of angular momentum requires that a system contain a number of particles so that the sum of the two is equal to the sum of the individual particles after the interaction, the sum of the two before of interaction. And so in summary, it appears that neutrino is required in order to save no less than 3 conservations law: mass energy, which we talked about it, mc squared, linear momentum. So if this was happening, then momentum would be, and angular momentum. Okay. So, however, when we, if beta positive, which is the particle, antiparticle of the electron is produced, then what is happening is an anti-neutrino is formed. So when we have an a proton now 1 1 that is it is transformed into a neutron, 0, 1, and a beta positive or a positron, beta positive, the same thing, and then an antineutrino is formed. The antiparticles are written with this line on top here, which are telling that are antiparticles of each other. When we talk about the antiparticles, what it is that the they have the same characteristics. So the definition of the antiparticle is they have the same characteristic, but the opposite quantum number. And quantum numbers are different. The one that we have used widely in physics 30, however, one that we haven't specified as a quantum number is the charge. So if we have an electron, we know that the mass of the electron is, so if we have an electron, then we know that the mass of the electron is -1 elementary charge. And it is, charge is -1 elementary charge, and mass of the electron is 9.11 times 10 to the power of -31 kilogram. The antimatter of the electron is something that is known as the positron, and the charge of the positron is +1 elementary charge, and the mass is 9.11 times 10 to the power of -31 kilogram. So everything else is, besides the quantum number, everything else is the same. Okay, when we have a beta negative, again, if we summarize now, beta negative decay involves a transformation of neutron into a proton beta negative and a neutrino. And in general, if there is an element that is decaying a beta negative, then what we will have is element X, that is the pattern element, parent element with mass, atomic mass A and Z, is releasing a beta negative, then a new element Y with Z plus 1 and A atomic number is formed, and then a beta negative decay, which you can write electron is the same thing, and neutron is produced. And when we have a beta positive decay, so beta positive decay, then it is transformation of a proton into neutron and a beta positive. So proton 1 is transformed into a neutron 0 1, a beta positive, which you can say positron or electron plus 1, and an anti-neutrino is produced. And if we have an element that is releasing a beta positive, element ZA will be forming an element Y that is Z minus 1A, and a beta positive and an anti-neutrino. Okay. Gamma radiation, on the other hand, which is used widely in medical field, it is a photon, so it's not a particle on its own. And this is why when it is into the magnetic field, it doesn't even interact with magnetic field at all. It goes straight to undeflected. And they have a high energy power because they are short wavelengths, therefore high frequency, which are giving us based on Planck's equation, high energy. In terms of the dangerous hazard that those radiation are creating, are affecting our life, this is a table where we even talked about this when we are talking about alpha particles. It is able to travel about 5 centimeters in air, and it cannot penetrate into the skin, so it is not that dangerous. Ionization is high, however, the hazard is not that high. Beta, this beta positive or beta negative, they both travel about 30 to 50 centimeters in air and have a low penetration into our body. Then we can go 2 to 3 centimeters into an aluminum foil or aluminum block, and the hazard is as well low, while gamma, they can travel up to 2 kilometers and they can penetrate right through the body of human being. And the ionization is a low, but hazard is a very, very high. Next one will be the half-life decay. Next topic that we will treat now is half-life decay. Radioactive elements do not decay all at once, so they decay at depending on the time, and the way that they are governed is with a logarithmic, or in other words, with an exponential equation. So the function that governs the decay of an element is n equal NO 1/2 n, where capital N is the number of radioactive nuclei remain. So number of nuclei remained, or mass remain, or the material remained. N0 is a number of initial nucleus, original nucleus. Okay. N is the number of half-life. The number of half-life. So it's pretty much is the time, N is the time that you are measuring what is remaining over the time of half-life that may be given, or maybe you may find it. So let's suppose that what we have here is, we'll bring it. Here is legend, whatever is colored, it's considered to be parent nuclei, and whatever is empty, that's considered to be daughter nuclei created. So if we start with a certain time, then we will have 100% of the nucleus are from the same type as the parent nucleus, and the 0% will be daughter nuclei. However, when we have 1/2 lifetime, and that may be years, maybe even decades, but even maybe minutes, then half of the nucleus now are becoming daughter nucleus, and half are staying as parent nucleus. And then when we have two half-lives, then 25% are staying as parent nucleus, and 75% are staying or becoming daughter's nuclei. Why 25%? Because it is half of 50. Okay, half of 50%. So let's suppose that if we have 100 nucleus, then parent nucleus are 25, and then parent nucleus for the second half-life become half of the previous one, which is half of 50 is 25, and half of 25 is 12.5, and so on and so forth. So when we are considering the half-life, this is what we keep in mind. So it's the formula is this one here, and the concept or the understanding is this picture here. The half-life can range from trillions of seconds to years. This is totally dependent on the stability of the isotope. So if we have a half-life of a radioactive decay, that is, so a half-life is 2.5 years. And the original the original sample is 3.2 times 10 to the power of 3 number of nuclei. What is the number of nucleus at 5 years? So now the lowercase n, which is the number of times in the half-life, will be t, that is the time in which you are observing it. In our case, it's 5, and t of half-life. So 5 years, what is important is that the units of time has to be the same. Over 2.5 years, it doesn't matter what are the units, so years and years will cancel out. Then this will be the same as saying 2. So now the number of nucleus remaining will be 3.2 times 10 to the power of 3 times 1 over 2 to the power of 2, and it is 8.0 times 10 to the power of 2 nucleus remaining after 5 years for this particular element. And if we have an example in which the sample or the original amount is given in grams, so let's suppose that sample of radioactive isotope goes in a radioactive decay, and the original mass is 2.0 grams. Then the half-life is 45 minutes. And how much isotopes are remaining after 5 hours? So how much isotopes are remaining after 5 hours? So n is equal to n0 1 over 2 n. Let's find what is the number of half-life time in the time that we are looking at it. So we will have 5 hours over 45 minutes, or 5, as is important, as I said, to have them in the same units. Doesn't matter what units are they, as long as they are the same units, so that you can cancel it out. So n is equal to 6.67. And then we find n as 2 grams times 1 over 2 to the power of 6.67, and then n will be around 0.020 grams remaining after 5 hours. Okay. Now let's figure out, or let's have an example in which we are finding what is the half-life. So if we have an element with a sample that is 28, so it starts at 28 nuclei, and then After 8 hours, it becomes 7 nuclei. After 8 hours, what is the half-life time of this radioactive decay? So the formula is n over equal n0 1 over 2 n. So, and within this we have t over t and 1.5. So the whole point, or the first step, the intermediate step, will be to find what lowercase n is. So what we'll have is, what we will have is 7 over 28 is equal to 1 over 2 to the power of n. And from here we find that n is equal to, because this is same as saying 1 over 4, n is equal to 2. So if n is equal to 2, on the other side, what do we know is that n is time over the half-life time equals to 2. And then now we know that t is 8 hours. So 8 hours over t and 1.5 is equal to 2. From here, t 1.5 half-life is equal to 4. 8 over L over 2 is equal to 4. So it's 4 hours. The graph that represents the half-life is something like this, where n is this one here and time is here. So if we have one half-life, then we will have n0, and then 2 half-life will have half of n0. So let's make n0 here. So half of n0 will be here. And the line will be this one here. 3 half-life will be half of it. So this point here, we start here. 4 half-life will be half of it. 5 half-life will be here, will be half of it. This point here, 5, 6, and so on. So the graph will look something like this. Okay, so it is a graph in which they have as the asymptote the horizontal axis or time axis, which means that it never intersect and it never touches the time life. So it doesn't matter how much time it goes through, it still will have some material remaining them, either nucleus or amount or whatever we have in starting with. So this graph will be a nice one like this. Okay, this is the lesson for today, and I will see you on the next one, which is the last lesson for physics.